Right now, a neutrino is going through you, through your chair, through the floor, through the entire planet. And it will never even notice you were there. Here's why. A neutrino can cross your body or the whole Earth the way you'd walk through a stadium packed with people if every single one of them happened to be a ghost. Which sounds like a party trick until you realize what it actually means. A neutrino can travel from the most violent places in the universe, the ones so thick with matter and radiation that light can't punch its way out, and arrive here almost completely undisturbed. A neutrino carries a clean signal from someplace that would scramble anything else you sent to it. That's the gift. Here's the curse. If it barely interacts with anything, how do you catch it? Physicists answered that question by building a telescope in the last place I would have gone looking for one. Under Antarctica. IceCube is a quarter of a cubic mile of Antarctic ice wired into a particle detector. 86 strings over 5,000 light sensors dropped into holes bored close to 1.5 miles down and left to freeze in place. There's no mirror, no dome, no eyepiece. The ice itself is the instrument, and almost nothing happens in it. That's the whole design problem. IceCube isn't watching for neutrinos, it's waiting for years at a time for the one in an astronomical number moment that a neutrino actually clips something inside all that ice. When it does, that collision kicks off a charged particle, and that particle can move faster than light moves through the ice. Not faster than light in a vacuum, so Einstein's fine. But light slows down going through a dense medium, and a fast enough charged particle can outrun its own light in that medium, the same way a jet outruns its own sound. A sonic boom for light is a cone of blue glow, Cherenkov radiation. That's the entire engine IceCube's built to get. One blue flash, buried in a cubic mile of ice, going off maybe a few times a day. Every sensor near that flash logs two things: when the light hit it and how bright it was. That's it. IceCube never actually sees the neutrino. It sees a few thousand tiny stopwatches firing in sequence, rebuilds the direction and an energy. Two different shapes come out of that. A muon draws a long streak clean through the detector. Sensor after sensor lights up down the line. Great for pointing because a line tells you where it came from. A cascade lights up all at once, like a flash bulb going off underwater. Much worse for pointing, but it hands you a much cleaner read on the energy. Same flash, two different questions answered. Then there's the noise problem. Cosmic rays are slamming into the Earth's atmosphere constant, showering down secondary particles that would drown out a real neutrino signal in seconds if IceCube were sitting exposed on the surface. A mile of ice overhead filters most of that out on its own. But the real trick is bigger than that. The planet itself is a filter. A neutrino can pass straight through the entire Earth and come up through the ice floor from below, and almost nothing else can survive that trip. So IceCube's most trustworthy neutrinos aren't the ones raining down from the sky above the South Pole. They're the ones coming from underneath, which means when the detector looks down, it's using the whole Earth as a lens, watching the sky on the other side of the planet. In September 2017, one of those neutrinos came through carrying enough energy to matter. The reconstructed line pointed back to a blazar, a galaxy with a supermassive black hole firing a jet of particles almost directly at us. Gamma ray telescopes checked that patch of sky. The blazar was firing, active, lit up at that exact moment. One ghost particle, one coordinate, one galaxy caught in the act. Nobody is claiming that solved high-energy astrophysics. What it did was smaller and, honestly, more convincing. Completely different kinds of observatories, watching two completely different signals landing on the same object at the same time. And here's something worth thinking about. None of the light in that story came from the blazar. Every photon IceCube saw was manufactured locally inside the ice by a particle the neutrino kicked loose on its way through. The neutrino is just the messenger. In fact, the blazar never sent a flash. It sent a ghost. and the flash got built 4,000 miles away in the dark under a continent that never sees the sun for half a year. That's the whole advantage neutrino astronomy has over regular astronomy. Photons get absorbed, scattered, blocked by dust and gas and each other. Neutrinos mostly don't notice any of us there. The price for that is brutal because you need an ocean of detectors just to catch a handful of them doing anything at all. IceCube's answer to that price tag was to stop trying to build a detector and just claim a quarter cubic mile of ice that was already sitting there for free. The sun is also full of neutrinos. Lower energy, nowhere near as dramatic, same underlying deal. A photon born in the sun's core can spend 100,000 years bouncing its way out before it ever reaches the surface. A neutrino born in that same reaction just leaves immediately. No detour, no stop. So every one of these detectors, whether it's watching a blazar 4 billion light years out or the star 93 million miles from your driveway, is doing the same job, catching a second whiter light from places where the first kind can't get out fast enough. A telescope doesn't have to be a tube pointed at the sky. Sometimes it's 86 strings and 600 new sensors frozen 1.5 miles under the South Pole, sitting in the dark for years, waiting on a particle that crossed the galaxy, crossed the Earth itself, and finally decided to touch one single atom of ice. One blue flash, and just like that, the ghost has an address. Eyes up and clear skies.